session, Alex Damian will give the first talk. He came all the way from Princeton, and he's going to talk about learning from Gaussian data, single and multi-index models. Thank you, Alex, for coming, and take it away.
Yeah, thank you so much. I want to thank the organizers for the invitation, and I'll be talking about a longer series of works on learning from Gaussian data. So this is a question that people have been working on for quite a few years now to understand different aspects of computation, statistics, and just what we can expect to get out of Gaussian data. And so in the first part of the talk, I'll focus on single index models, because that's where the math is at least the cleanest. But then in the second half of the talk, I'm going to move towards multi-index models, since those questions just are more interesting. So to start, what I mean by a single index model is that I'm going to assume all the data is Gaussian, as I mentioned, and then I'm going to assume that the labels y only depend on the inputs x via their projection onto some unknown hidden direction w star. So here z denotes the projection of x onto w star, so w star is a unit vector, and we're assuming that the distribution of y conditioned on x only depends on z. So here, d denotes the input dimension, and throughout this entire talk, I'm going to assume that d is very large. So we're interested in the case where we have a single index model in very high dimensions, and our goal is going to be to recover this high dimensional hidden vector w star. So we're going to be given a bunch of observations, xi, yi, from this model. So just for some easy examples, the easiest is if you just have a linear regression problem. So here y is just a linear measurement, x.w star, and you can add some noise on top of that if you want. So this would just be linear regression. You can have a more interesting setting, which has been studied, called phase retrieval, in which you put an absolute value after you perform the linear projection. You can also square the input, so it could be x.w star squared. This would also be OK. And more generally, you can just consider this problem of learning a single neuron. So if I take this low-dimensional projection, z, and then I apply some nonlinearity to it, sigma, and then I add noise to that, you could call this learning a with-one neural network if you want. And finally, you can also do really weird things, because I never said that it had to be of the form sigma of x.w star plus noise. So here, for example, I could take x.w star and multiply it by a random Gaussian. So now y has mean 0. So the conditional expectation of y given x is 0. But it's still a valid statistical model, and it turns out that you can recover w star efficiently from these observations. So the question that I'm interested in this talk is how many samples xi, yi do you need to see if you want to actually recover this hidden direction w star? And if I'm just asking about sample complexity, this is actually a very classical question. So you can easily just check what the information theoretic rate is, and by some standard covering number argument, because the covering number of the sphere is exponential in d, you take its log, then you get that order d samples suffice if you want to learn w star. But this doesn't really come with an algorithm. Or it kind of does, but the algorithm that it gives you is you kind of net the sphere and then check exponentially many points on the sphere, and you look for the weight w that has the best fit to your data. This is not really an algorithm. It requires exponential time, and you could never actually implement this in practice. And so the question really is, how many samples do you need to efficiently recover w star? So let's say I'm restricting myself to polynomial time algorithms. I want something efficient. And the question is, can I still learn with order d samples? And the answer turns out to be no, at least not always. So in order to describe what type of mathematical structures show up and what actually determines the sample complexity of learning, I need to do a brief aside and do some background on Hermite polynomials. So these have turned out to be a really important tool, and it makes sense that these show up because we're dealing with Gaussian data. And this is probably the strongest tool that we have for dealing with Gaussians. So here, the Hermite polynomials are the orthogonal polynomials with respect to the Gaussian measure. So here, I've normalized them to all have variance 1, and I've just plotted the first, or I've just shown the first 4 Hermite polynomials. And the important property that these polynomials have is that they're orthonormal. So if I look at the expectation of hj and hk for j and k different, then this will just be 0. But as I mentioned, the variance, so expectation of hj squared, will be 1. So these form an orthonormal set with respect to the Gaussian measure. And this actually lets you do something very powerful, which is if I give you a function, which is not necessarily a polynomial, I can always write it as an infinite series, and it's going to be a sum of Hermite polynomials. So formally, this expansion is an L2, but you can always take some f and decompose it as a sum of Hermite polynomials with some coefficients. And these coefficients are given by taking the inner product between my function and the kth Hermite polynomial. So now I can write anything in terms of Hermite polynomials, and now this lets me take inner products between functions very easily, because the Hermite polynomials are orthogonal. So just to give some examples, the linear function x is just already the first Hermite polynomial, so if I'm writing out this infinite series, that's the only term that remains. But the next thing that I mentioned was absolute value of x. And this one has really crazy coefficients that have square root of pi's in random places, but you can compute it explicitly, and it has like a 0th Hermite coefficient, a 2nd, and a 4th, but it doesn't have a 1st and a 3rd Hermite coefficient. And this kind of makes sense because these are polynomials. If you remember from the previous slide, the 1st and 3rd Hermite polynomials are odd functions. Absolute value is an even function, and so it kind of makes sense that they shouldn't show up in the expansion. But there turns out there are a lot more reasons why some Hermite polynomial might not show up in the Hermite expansion. So next, x cubed minus 3x is just a rescaled version of the 3rd Hermite polynomial. So this is, again, just going to be non-zero in this 3rd row, or 3rd column, and it's going to be 0 everywhere else. And finally, you can cook up some really funny functions. So this one, x squared e to the minus x squared, when you write out the Hermite decomposition, the 1st, 2nd, and 3rd terms are all 0, and the first non-zero one after the mean is the 4th Hermite polynomial. So it turned out that you can take your activation function. So if you're looking at labels of the form sigma of w dot x, then I can take sigma and Hermite expand it. And the relevant quantity that shows up when you're actually trying to analyze optimization and statistics is this idea of the information exponent, which is defined by Gerard Benarus and co-authors. So the information exponent, which throughout the talk I'm going to denote by L star, is the first index that's at least 1 that has a non-zero Hermite coefficient. So because I'm restricting that the index has to be at least 1, I'm going to zero out the first column. I'm not going to look at it. And then the information exponent is just going to be an integer that tells me where I find the first non-zero entry. So in this case, for x, it has information exponent 1. Absolute value of x has information exponent 2. X cubed minus 3x has information exponent 3. And x squared e to the minus x squared has information exponent 4. So this is something you can easily compute. If I give you an activation function, you can write a Mathematica script or something to compute these coefficients, and then easily check what its information exponent is. But why do we care? So why is this exponent actually important? So the first thing is that it's a barrier for a lot of natural methods that you could try for learning W star. So as I mentioned at the beginning, if you just try and actually implement this maximum likelihood estimator, you essentially have to grid search the entire sphere, which is just not computationally efficient. So now you could say, okay, what are computationally efficient methods that we do have for recovering W star? And one very common one is something like a method of moments. So you try and estimate some tensor, like expectation of y times x tensor k, and then you hope to recover W star from this tensor. But the problem is that you can easily show that if the information exponent is large, you have to look to a very high moment for this tensor to not just be identically 0. And so this is already challenging because these problems get harder and harder as the order of the tensor increases. It's also a challenge for gradient descent. So if you just want to look at the initial gradient for gradient descent, if you come up with an optimization problem and then you just stare for as long as you can at the initial gradient and you want it to concentrate, then this concentration actually requires d to the k star samples, sorry, d to the L star samples. And so now, instead of getting a linear number of samples, you can actually get these really bad polynomials in the input dimension for the number of samples that you need to learn with gradient descent. And it turns out with a more careful analysis, this L star is not tight, and it can be improved to L star minus 1. This is, again, this paper by Gerard Benarus and co-authors. But this is also not optimal. So this can be improved via some analogies to the tensor PCA literature using smoothing. So I proved a few years ago that if you actually run online SGD with smoothing, so you are explicitly smoothing the loss landscape, then you can learn with L star over 2 rather than L star minus 1. So the takeaway from this whole line of work, this was a very, very long line of work, but the takeaway was that if I give you some single index model, there is some exponent L star that you can efficiently compute, and this exponent L star determines the sample complexity of learning for many natural algorithms. So just to compare these two, online SGD was L star minus 1, smooth SGD was L star over 2. So you can ask, like, is this optimal? Like, is this the best we can do? Because this is telling us that there are some functions that are just really hard to learn. So at the beginning, if you just take like a higher order Hermite polynomial, this is saying that you might have to pay some arbitrarily large sample complexity in D. Whereas I said that information theoretically, all of these problems are learnable with order D samples. So with a linear number of samples. So this seems pretty bad. And the easiest observation is that it's clearly not optimal. And the reason it's clearly not optimal is that this idea of a Hermite expansion and this information exponent is not invariant to transformations. And what I mean by that is, take a very simple example, which is the 10th Hermite polynomial. So this is just a degree 10 polynomial that has information exponent 10. Because if you write out its Hermite expansion, the only non-zero term is the 10th term. So this corresponds via smoothed SGD to a sample complexity of d to the 5th samples. But this is not optimal because I can square it. So if I take this polynomial and square it, I'm going to end up with a degree 20 polynomial. And then this is going to turn out to have information exponent 2. This is not a very difficult calculation. You can easily check this, or you can make Mathematica check this. But the point is that if I can square it, then it immediately gives me an algorithm for learning with linear number of samples. So I start with my xy pairs, and then I begin, before I run any algorithm, by just squaring all of the labels. So I'm allowed to do that. And now it's as if I was given samples from a single index model in terms of g squared rather than g. So now I can run whatever algorithm I want. I can run online gradient descent or smoothed SGD. And because now the information exponent is 2 after squaring, I can learn with a linear number of samples. So this is a powerful trick. You start with some problem that looks hard, and then by applying some nonlinearity, you do much better. So this was studied very carefully in this paper by Marco Mondelli and Andrea Montanari, where they actually characterized explicitly when this trick works. And OK, maybe you don't have to square the labels. Let's say I allow you to apply some other nonlinear transformation to the labels. But the goal is I'm given a bunch of labels, and maybe the original problem is hard, but I want to apply some sort of nonlinearity to the labels so that the result is easy. And by easy, I mean that it has information exponent at most 2. So the theorem here is that there exists a label transformation T that I can apply to each of my inputs, such that after I apply the label transformation, I have information exponent 2, if and only if some very funny condition holds. Something has to be non-zero in L2. I'm going to come back to this condition. It looks a little strange. But then the punchline is that if this thing is actually non-zero, then you can recover W star with ordered D samples using a spectral estimator. And importantly, the way the spectral estimator works is it first applies this nonlinearity T to each of the labels, and then it runs the spectral estimator on the result. And this exact same condition, this very funny looking condition in terms of this conditional expectation, turns out to be a barrier for approximate message passing also in this proportional regime when n is proportional to d. So it seems like a fairly fundamental constraint for learnability. So I want to talk a little bit about what this actually is saying. So what's the bad case? What's the bad case in which no such transformation exists? For no such transformation to exist, you would need this object T2 to be identically 0, because I'm asking for the expectation of something squared to be non-zero. So the bad case is when it's identically 0. So it's essentially saying, kind of rearranging things a little bit, that for every label y, if I condition all of my data set on having this label, and I look at the variance of the inputs, this variance should not be always 1, identically 1. So pictorially, if I have some activation function, in this case I'm picking this funny one that's z squared e to the minus z squared, and I take some level set, so I'm fixing some label y, then I look at where this intersects, and this gives me this distribution of z given y. So this distribution of z given y, the conditional distribution, will be supported on these 4 points with some weights. And what I'm asking is that this distribution does not have variance 1. And actually, it's OK if it has variance 1 for this y. But as I vary y, it's important that at some point, for some y along this line, the variance is no longer 1, because that will be enough to guarantee that this T2 is not identically 0. So it's really some sort of constraint on the level sets of my function. So OK, this is nice. It tells us that when you can learn something efficiently by lowering it to information exponent 2. But it turns out that this function that I just showed you actually is the bad case. So for this specific function, you can check that if you compute these level sets, and then you actually compute the variance, it is actually identically 1. And this is not an accident. I had to work to cook up this function. But if you look at this function, it is this bad case, which means that there does not exist a label transformation that will allow me to lower the information exponent to 2. So this function is actually hard to learn, at least under this machinery. So it should be hard to learn for AMP, and it's hard to learn for a spectral estimator. So can we still learn it? Like, do we have any hope of learning a function that looks like this? So it turns out that you can generalize this idea to higher order and ask, when can you find a label transformation t that will lower the information exponent to some higher number, k? So maybe I can lower the information exponent here to 3 or 4 or something. So the variational definition of what we're calling the generative exponent, k star, is that it's the smallest information exponent that you can achieve via a label transformation. So here I'm searching over all possible label transformations that I can apply to my data. For each label transformation, I'm computing this information exponent. So I'm doing the Hermite expansion, and then I'm looking for the first non-zero coefficient, and I'm taking the infimum over all such transformations t. And this will be some integer. So in the previous slide, we looked at the situation where this generative exponent was equal to 2. But it could be much larger in general. So this is kind of annoying because it's a variational definition. I have to optimize over these label transformations t in this infinite dimensional space. But you can give a more direct definition, which is exactly like this paper from Marco Mandelli and Andrea Montanari, which essentially just replaces this z squared minus 1 with the kth Hermite polynomial. So what this is now saying is that I'm still looking at the same level sets, and I'm saying, OK, maybe the variance of each level set is 1, so that I can't just lower it to information exponent 2. But maybe I can look at higher moments, and you check how many moments does it agree with a Gaussian for. So if the first moment is 0, the second moment is 1, the third moment is 0, the fourth moment is 3, then that tells you that this T4 will be 0, because it agrees with too many moments of a Gaussian. So this is a more general definition, and we can now ask, like, what does this look like for some reasonable functions? So what is the generative exponent? So for one example, all polynomials have generative exponent either 1 or 2, and it's only 2 if the polynomial is exactly even. So this is already somewhat surprising, because the hard case before, the things that had very high information exponent, were exactly Hermite polynomials. I could take a very, very high order Hermite polynomial, order 100 Hermite polynomial, and this should be hard to learn because the information exponent's 100. But it turns out that after a label transformation, you can learn it in a linear number of samples. So polynomials are actually very easy to learn. So this kind of funny example I showed earlier, z squared e to the minus z squared, this has generative exponent 4. So while we couldn't learn it with order d samples using the spectral estimator, there is an algorithm that learns it with order d squared samples. And finally, we actually cooked up some really hard examples where for any integer k, there is some really strange activation function sigma that has generative exponent k. And I'll show you some pictures of these in a few slides. But that means that the sample complexity actually can scale arbitrarily bad. So the reason that we care about the generative exponent, in addition to the fact that it gives us some like clean upper bound for when we can reduce the information exponent to something small, is that it turns out to be the tight characterization for this problem. So the theorem that we managed to prove is that, I'm just restating the definition here, but the theorem is that d to the k star over 2 plus d over epsilon samples are both necessary and sufficient to recover u star up to error epsilon. So I have an asterisk next to the necessary, and I'll get to that in a second. But the first thing is that this number of samples is sufficient, and this is the easy direction. So how would you learn a single index model if you knew its generative exponent was k star? Well, the first thing you would do is say, I know that there has to be some label transformation out there that reduces the information exponent to k star, so I'm going to look for it and then transform the labels. So the first thing I'm going to do is exactly this trick where you square all the labels or apply some nonlinear transformation to the labels. And now I'm in a setting where the information exponent is low, because I've applied this transformation. So then I can just run something like smoothed SGD, which gets d to the k star over 2 sample complexity. And this will give me this upper bound. Great. So this is a generalization of the spectral estimator in Marco's paper. So what about the lower bound? So I'm claiming necessary. And necessary is kind of a crazy thing to say because I said at the beginning of the talk that order d samples could be done in exponential time. So here by necessary, I really mean necessary for polynomial time algorithms. But that also doesn't make any sense, because there's no way I can stand up here and tell you that I have a lower bound against all polynomial time algorithms. That would be a refutation of p equals mp. So instead, the way people generally attack these types of things when you want to argue that something is hard computationally is you look at some restricted models of computation. And here specifically, the models of computation that we're looking at are the statistical query models and the low-degree polynomial models for computation. I'm not going to have time in this talk to go into exactly what these are, but they're a fairly powerful class of algorithms that include stuff like gradient descent for a constant number of steps. It includes approximate message passing. It includes spectral methods. So any natural algorithm that you could imagine using to recover W star will not work. And you really have to do something crazy to escape these classes, because they're really general classes. So, OK, let me give some examples for what these label transformations look like. And these are just because the plots are really pretty. So here what I'm plotting is the density map of the fifth Hermite polynomial when the input is Gaussian. So on the x-axis, I'm plotting here, this is the marginal of my input, z, this one-dimensional projection. And then I'm applying this Hermite polynomial with some noise. And then for the y-axis, this is the marginal distribution of y. And here on the middle, you see the joint distribution of z and y. So the problem here was that this had really high information exponent. So I claimed that there was some transformation that would lower this to 1, because all polynomials have generative exponent 1. So it turns out to look like this. I'm not sure why it looks like this, but it seems that for whatever reason, the values of y that are close to 2, you want to shrink to -2. And then the values of y that are close to 3, you want to flip. But after you apply this transformation, this polynomial ends up looking like this. So very different from what it initially looked like. But this is very easy to learn, whereas that was very hard to learn. So applying this transformation really helped. You can do the same thing with this multiplicative noise model. And here the failure is actually even worse. Because here the information exponent is technically infinite. Because I'm looking at a model that's like 0 plus noise. And if you Hermite expand just the 0 function, all the coefficients are 0. And so you'll never find a non-zero coefficient. So this turns out to have information exponent that's infinite, but it has generative exponent 2. And the idea is that you can apply this funny function. So squaring would work, but the optimal transformation is to do something that interpolates between square root and absolute value. And this will transform this into an activation that looks like absolute value, and then this is easy to learn. You essentially are reducing this problem to phase retrieval. So this was the hard example that I showed, z squared e to the minus z squared, that had information exponent 4 and generative exponent 4. So here there is some transformation that can improve the constant, but in general, you can't reduce it beyond 4. And finally, we were not the first to cook up an example like this that had generative exponent 4. So there was actually an example in this paper by Marco Mandelli and Andrea Montanari that looked like this. So this was the distribution that they gave. And there in that paper, they weren't thinking about the generative exponent, but all they claimed is that it didn't have generative exponent 2. So it violated their condition for when you could lower something to information exponent 2 via a label transformation. And it turns out that this function that they cooked up had generative exponent 4. And you can easily check this. So I also promised that we can go beyond 4, and there are some really, really hard link functions. And this is what they look like. So this is not an exhaustive family, but for any integer k, you can at least cook up some function that's very hard to learn. So if I give you samples from this model here, if this is your nonlinearity, then no polynomial time algorithm will succeed without d to the 4th samples, which is quite bad. But apparently, it's just a fundamentally hard problem. So just to conclude for single index models, we introduced this idea of a generative exponent, and it's the smallest information exponent that you can get via a label transformation. And this also has a more direct definition rather than this variational definition. And we proved an upper bound that said that if I give you a Gaussian single index model, you can easily recover this hidden direction W star with a sample complexity of d to the k star over 2, and that this is optimal. So what this is telling you is that this really naive idea of like, oh, I'm looking at my labels, this information exponent isn't invariant to transformations, so I could square it and reduce the information exponent. This technique is optimal. You actually can't do any better than this. Like, it sounds very simple, but the optimal algorithm for learning a single index model is to apply a nonlinear transformation and then apply something like smoothed SGD. So that's it for single index models. And now I want to talk about a more interesting but mathematically more challenging class of models, which are multi-index models. So The only difference between a single index model and a multi-index model is that rather than only depending on a single projection into one unknown hidden direction, we're going to be projecting onto a subspace. So here U star is going to be a subspace of dimension R, and I'm assuming that my labels Y only depend on my inputs X via their projection onto this unknown subspace. So if the dimension of this subspace is 1, then you're just projecting onto a hidden direction, and it's exactly the same as the single index setting. But now R could be much larger, and you could depend on multiple directions in your input. So to give some examples, we're going to actually see that one of the hard functions, the equivalent of like a Hermite function to learn, is Gaussian parity. So I'm going to take a bunch of random projections into R orthogonal directions. I'm going to compute the projection of my input onto these directions, multiply them, and then take their sign. And so this is an extension of Boolean parity to the Gaussian setting. We can also just look at something like a deep neural network. So this is essentially assuming that if you have a neural network, that the first layer of the neural network has rank at most R, which tells you that it's projecting into some unknown R-dimensional subspace, and then after that, you can do whatever you want. So after I've projected into R dimensions, I can apply the most complicated transformer architecture that you want, and it would still be a Gaussian multi-index model. And finally, a very popular thing that the TCS community has been looking at is intersection of half spaces. So information theoretically, these problems are still not that interesting, because every single multi-index model can be solved essentially in order d times r samples. And this is because if you look at the number of subspaces of dimension r, and you look at the dimension of this space, it has dimension d times r. So if you do a covering number argument, then you can kind of net this space and look for the optimal U star. But again, this like brute force algorithm that I'm going to search for every possible subspace and look for the right one really requires exponential time. And so it doesn't give us an actual algorithm that we can compute. And so the question that we want to answer is how many samples do we need to efficiently recover U star? So again, in the setting when r equals 1, this gave rise to this idea of the generative exponent. And so now, because r equals 1 is a special case, we're going to have to come up with a generalization of the generative exponent for multi-index models. So the first key ingredient came from this really, really beautiful series of works by Manuel Abe, Enric, and Theo from 2022 and 2023 that they called the staircase property. So the starting point for the staircase property is that there are actually some multi-index models that are just hard to learn. And as I mentioned before, Gaussian parity is an example like this. So here, the challenge is essentially that you need to learn r directions at once. And if you get any of them wrong, even a little bit, then you get absolutely no signal. So mathematically, this corresponds to an order r saddle in the optimization dynamics. And so these are very difficult to escape, and it turns out that you need a lot of samples to escape such saddles. And so when you just analyze gradient descent or online SGD, you need something like d to the r minus 1 samples. And so the difficulty of parity scales very quickly with the number of unknown hidden directions. So this function is hard to learn. The polynomial can scale very badly. But it turns out that just the fact that you have something like Gaussian parity in your multi-index model is not a death sentence. And what they introduced in this series of works is this idea of a staircase function. So here I'm going to start by defining the staircase functions in a very simple setting, and then I'm going to show how it generalizes to any multi-index model. So the staircase function, the easiest staircase function to think about looks like this. So it's going to be a sum of Gaussian parities. So I'm going to look at the sign of z1, the first coordinate, and then I'm going to add to it sign of z1, z2, then sign of z1, z2, z3, et cetera, until I work my way up to full parity. So turns out that this function, this staircase function, is much easier to learn than Gaussian parity. And there's a very simple algorithm to see why this is. So the first is pretend for a second that none of these higher order terms existed. So you just really have the first term, sign of z1, and you just wanted to learn this. This, if you think about it, is really just a half space. It's really just saying that there's some direction that we don't know, and on one side of this direction, the sign is going to be 1. On the other side is going to be -1. So you're just learning a linear classifier. This turns out to, I mean, this is clearly doable with a linear number of samples, but also in the language of information and generative exponents, it has exponent 1. So this is an easy problem. If I just gave you this, you can learn with order d samples. And I can now recover this direction z1. And it turns out that the existence of these higher order terms doesn't really hurt you. So you can actually just run the same algorithm that you would run to learn a half space, and you can treat the rest as label noise, and this is safe. So OK, we've managed to recover one direction, but now what? Because we said that this was really hard. The full parity was really hard. But the idea is that we've now kind of learned part of it. We've learned the direction z1, and we know it matters. So here you can do a very explicit trick. In general, there's like a more general thing you can do. But here, just for simplicity, I'm going to say that we should multiply all of the labels y by the sign of this coordinate that we've just learned, and then subtract 1. So what happens when we do this? If you take this expression and multiply it by the sign of z1, the first term will just become 1. The sign is always either +1 or -1, so if you square it, it's just 1. So this term becomes 1, and I'm subtracting 1, so it disappears. So the first term is gone. And then for the rest of the terms, sine is a multiplicative function. So this is equal to sine of z1 times sine of z2. And so when I multiply it by sine of z1, the z1 just drops out. And so effectively what this trick is doing is it's taking every term in this expression and deleting the z1 term. And this is just free, because we've learned the right direction. And so now we can reduce it down to a staircase function that has r minus 1 unknown variables. And now we can play the same trick. Again, the lowest order term is a half space. You can learn it in order d samples. So we learn it, we multiply all the labels by sine of z2, and subtract 1. And you keep doing this until you're left with a single half space, sine of zr. Again, this is easily learnable, and you're done. So although we kind of built up to Gaussian parity, and Gaussian parity was one of the terms in this function that we were trying to learn, it turned out not to be very hard to learn, because we can kind of like bootstrap from previous things that we've learned, and easier things to learn. So just to give a cartoon for what's happened, you have this very hard function, which is Gaussian parity. And here, because Gaussian parity requires learning r new directions all at once, I'm going to kind of informally for now say that it has leap r, meaning that you need to, it's like a very challenging function to learn. And leap r, in terms of sample complexity, you should think of as corresponding to sample complexity d to the r over 2. So here, this is a hard function to learn. But what we did when we turned this into a staircase function is that we kind of flattened it out and allowed our learner an easy sequential learning procedure to build up to full parity. So the idea is that each step in this staircase has leap 1. And so for this learner to start and learn sine of z1 just needs a linear number of samples, because leap 1 is easy. And then once I've learned sine of z1, I can take the step up to z1, z2. And I can continue and continue until I've actually learned full Gaussian parity. You can think of this as some sort of curriculum that makes it easy to learn very hard functions. So in this way, we're able to learn this complicated function in a linear number of samples. But it doesn't have to be of this exact form. So you can consider other staircase functions with different leaps. So for example, if I delete some of the intermediate terms, I can get a staircase that looks like this. So here I'm looking at z1 plus sine of z1, z2, z3, z4. And so what you should expect could happen is that I'm first going to learn z1, and this is leap 1. And then once I've learned z1, I can kind of condition on it. And this function here turns out to only depend on 3 variables. And so this will end up being a leap 1 followed by a leap 3 rather than a leap 4. So here the sample complexity is going to be d samples to learn sine of z1, and then d to the 1.5 samples to learn the rest of it. And if you add these up, the total sample complexity for learning this function you should expect is d to the 1.5. It's also not true that these leaps have to even be connected. So if I make them disjoint subsets, so sine of z1 plus sine of z2, z3, z4, these don't share any coordinates. And so learning sine of z1 doesn't help you learn the rest of the function. So here, I can take this step onto sine of z1, but it doesn't help me get anywhere. And so I need to climb this one, and then I need to climb this one independently. So here, this has leap 3, even though we have a staircase function, just because they don't share any coordinates. Got it. So I want to go back very quickly to this setting here, where you have sine of z1 plus sine of z1, z2, z3. So here, I've just been playing with these Gaussian parities, but not all multi-index models are Gaussian parities. Like I claimed that you could apply this to a transformer. This is clearly not a transformer. So what do you have to do? So one thing that can actually make this much harder is if I replace the sine of z1 with a Hermite. So let's say I have the 5th Hermite of the first coordinate plus the sine of z1, z2, z3. Now this Hermite is very hard to learn. As I said, there's some like heuristic connection between the idea of a leap and sample complexity. So here, because the Hermite has information exponent 5, you need a lot of samples to learn it. So now we're just stuck. It's not actually helpful to learn this. And actually, it might be helpful to start on the other side. So the other thing is that Hermits are easily learnable in a linear number of samples. But you have to apply a label transformation to see that. And so the same thing applies in the multi-index setting. By applying some sort of label transformation to all of my labels, I can lower parts of the staircase and then learn more efficiently. So it turns out that this function you can then learn in a linear number of samples. So it turns out that any function can actually be decomposed in this way. So here it was kind of trivial examples, but for any multi-index model, you can always decompose the hidden subspace into an increasing sequence of subspaces, such that to go from one subspace to the next, it's some leap of size ki. And then the total sample complexity is going to be dominated by the maximum of all of these. And this is what we define as the generative leap. So the theorem that we have is that the number of samples that you need in order to learn a multi-index model depends precisely on the generative leap, and you need k star over 2 samples. And it's necessary and sufficient in the same sense that it was necessary and sufficient for the single index model. So sufficient meaning we have an efficient algorithm, and necessary meaning that we have a low degree lower bound. So the actual estimator that we use is a little complicated. So it's a little different from standard spectral estimators, and actually standard spectral estimators don't work. So we consider some sort of weird U-statistic matrix estimator. And this is pretty much required if you want to get the k over 2. But if you're OK with something weaker, like k minus 1, you can use a much simpler algorithm. But the way we actually do the learning is exactly by climbing the staircase. So here S represents the subspace that we've learned so far. At every step, we draw some number of fresh samples, compute this spectral estimator, and then look at its eigendecomposition and look at the top eigenvectors and add them to what we've learned. And now we've climbed one step of the staircase, and we just keep repeating, and here m is the number of steps in the staircase. So to give some examples before I wrap up, so as I mentioned, when r equals 1, the generative leap and the generative exponent just coincide. They're the same. And even in the multi-index setting, all polynomials have k star either 1 or 2. And this is actually known from this paper by Chen and Mecca from 2020, although in different language. So Gaussian parity has generative leap r, so there's no label transformation that can save you. And our upper bound actually gives the first algorithm, to the extent of our knowledge, that succeeds with d to the r over 2 samples. So it gives the optimal algorithm for Gaussian parity. So intersection of half spaces also have k star equals 1 or 2, so this is learnable with d samples. And finally, any piecewise linear function we proved has generative exponent 1 or 2. So this generalizes some prior work on learning deep neural networks, because if you take a neural network with ReLU activations, it is piecewise linear. And so this formalism actually allows us to learn any deep ReLU network with a linear number of samples without any knowledge about the network otherwise. So just to conclude, we introduced this idea of a generative leap as the generalization of the generative exponent to multi-index models. We proved an upper bound of d to the k over 2 samples using this weird matrix U statistic. And we proved that this is tight under the statistical query and low degree polynomial classes. And finally, we just instantiated this for a bunch of natural settings, including deep ReLU networks, and showed that a lot of these just have generative leap 1 or 2 and can be efficiently learned without having to do anything too fancy. So that's it for my talk. Thank you so much.
Really nice. Thank you very much. We have time for 1 or 2 questions. Let's start here.
Thanks for the talk. I'm interested about finding the transformations that you need for the labels. So if you don't have knowledge of the, like, is it a random transformation enough or?
Yeah, so if you do a random transformation, it will work with probability 1. I mean, it depends what you mean by random, but like random, like if you do like a random cosine or like something like this, it will just work with probability 1. You will get a worse constant. And so if you want tight constants, you need knowledge of the multi-index model or a single index model. But if you don't care about the constants and you just want the right dependence on the input dimension, yeah, you can do anything. I think even a random monomial will work. Like pick your favorite integer k, raise it to the kth power. This will probably work for any function.
OK.
Maybe following up on this, can you actually get constants when you do the tensor unfolding?
So our analysis gets constants, but constants are not a well-defined concept here. So in the case, no, like,
Velocity conference was last.
no, like, let me defend this. So it's the same thing as the gap between a spiked matrix model and tensor PCA, where for a spiked matrix model, there's this BBP transition. So you can say, like, there is this constant at which you get weak recovery, and below this you get nothing, and above this you start to slowly increase. But for tensor PCA, no such constant exists. So you need, like, d to the k over 2 signal strength or samples, but the constant can be continuously traded off with the runtime. So if you want to have the constant, you have to square the runtime. So it's a very poor dependence in the runtime. So the constant's like 1 over log runtime to some exponent. But getting a tight constant isn't really meaningful. Maybe you could ask some fine-grained question, like what's the best constant for a quadratic time algorithm? But I don't think we have tools for that. Yeah.
Thanks.
Oof, guys, okay. Also, let me, all the questions.
Hi. So if you have this sequence of staircase functions that you're learning, is there any kind of issue with like compounding statistical error with regards to like recovering one, then the next, then the next?
Yeah, definitely. So this is something that like our paper completely ignores, and I think every prior work on this is also completely ignored, where you're essentially assuming that the size of this multi-index model R is O of 1, and you kind of don't track the dependencies in R, but all of these algorithms have this implicit exponential in R dependency, and it's exactly because of this. Like if at every step you incur some error, then you take a bunch of steps on the staircase, and these compound, and you get this exponential blow up. I don't know if this is fundamental, but I actually suspect that in many settings it is. I think there are just multi-index models where if you want to learn them in a linear number of samples via one of these staircases, you just have to pay some exponential in R dependency.
Yeah, a very quick question. Can you say, like, can you apply this and say something about knowledge distillation? Just curious.
I'm not sure I follow the question, to be honest.
I mean, like, if I got it correctly, what you can say is something about, like, how difficult is it to learn a deep neural network? So maybe, like, there's a way to compare to if I have the raw data and if I have, like, neural network generated data. So that's what I thought.
Yeah, so I'm not sure distillation is the right language, but I think some sort of curriculum is more appropriate. So I think this is something that people have been thinking about in terms of, I don't know, chain of thought or getting transformers to reason better, where you want to start them off on easy problems and gradually increase the difficulty, because if you just give them hard problems to begin with, they have no chance. I think this is the strongest analogy with these types of staircases, where the idea is that once you've learned an easy problem, the next step, harder problem, is not that much of a leap, and so it's easy to learn, like sample complexity-wise, whereas if you just started with a harder problem, it'd be impossible. I'm not sure about like a distillation setting, though. Yeah.
Okay.
Hey, thanks for the really nice talk. When you define these staircase properties, like, how do you define it if the monomials share some but not all variables? Like, if you have like x1, x2, x3, and then x1, x4, x5?
Yeah, so here I was writing it in this like very axis-aligned setting, which was just nice for presentation purposes. And I didn't want to write the general formulas. Actually, I did technically cheat in this talk. I never defined the leap. I just kind of hand-waved a little bit. The actual definition turns out to involve the span of some tensors, and the idea is that to define a leap, k, given a subspace, I can define a leap relative to this subspace, which is like another subspace, and it's just the span of some tensor. And then you can take a union of these subspaces and iteratively build up from there. So if they share some but not all, it's like not really a problem for the definition. It actually doesn't even see this, but the actual technical definition is a bit complicated, so I didn't want to write it. I'm happy to write it down on the board later for you if you want. Yeah.
Thanks for the talk, very nice. Just one quick correction at the beginning. You said you cannot learn single index model with matching the information theoretic bound, but we prove in our result. In our paper with IMP, you do. So,
wait, sorry, say that again?
So you said at the beginning on single index model that you cannot learn these models with OD samples, but you can do it with IMP, and we do it in our paper.
No, but you have this assumption that it's the same assumption.
Okay.
It's
so
this.
What like you meant is when this condition is not verified.
Yeah, so you cannot always learn it. So the point is that, like, for example, AMP will never learn this function.
Okay.
Yeah.
I thought you meant in general.
No, they're clear, like linear regression is an easy situation where you can learn it with D samples. But I was saying that not all single index models are easy.
And so the actual question is about the last slide. You say you can learn these deep ReLU networks with OD. So what do you really mean? So how the, for example, the width of the network enters in the picture? Because
we're assuming that the width of the first layer is small. It's order 1. And then after that, I don't care what happens.
Okay, but you need this. Otherwise,
I need the first layer to be small.
Otherwise, I don't buy the results.
No, of course.
Okay, perfect.
Yeah, of course, of course. Like, it wouldn't be a multi-index model if the first layer weren't small. Yeah.
All right. After the second talk, I'm only going to take questions from the bottom half, so you better think of something now already. But first, let's thank Alex again.